This video is going to focus on polarity. And when we think about polarity, we want to focus in on covalent bonds. This is a type of chemical bond that is formed by sharing pairs of electrons. In this video, we're going to focus on both nonpolar covalent bonds and polar covalent bonds. Let's use a molecule that we're familiar with to review polarity. Let's start with water. So we know the molecular formula of water is H2O. And I'm not going to draw the electron configuration of water because we focused on that in a previous video. And instead, I'm just going to draw the structural formula of water. So in the structural formula of water, we know we have an oxygen atom that is covalently bonded to two hydrogen atoms. Both the oxygen atom and the two hydrogen atoms were originally reactive. They had unfilled valence shells. Oxygen had two unoccupied electron positions, while each of the hydrogens had one unfilled electron position, which means that oxygen can form two covalent bonds, each of the hydrogens one. And all three of these atoms can covalently bond together to form that stable molecule of water. Now, to layer on some more information on top of what we already know about covalent bonds, we can talk about the fact that covalent bonds can either be polar or nonpolar, and that is going to depend on the electronegativity of the atoms that are sharing these pairs of electrons. Electronegativity is defined as an atom's attraction to electrons, and these electrons can be the atom's own electrons or the ones that it is sharing with other atoms. Now, we're not going to get too detailed when it comes to electronegativity. There's a lot of information that goes into understanding the concept itself. But what I'm going to give you are a few tips, a few rules, so that when you are looking at atoms that are sharing pairs of electrons in covalent bonds, you'll be able to recognize which is the more electronegative atom. And let's use water as an example. We know that oxygen and hydrogen are sharing a pair of electrons, and it happens to be that oxygen and hydrogen have different electronegativities. Oxygen has the stronger electronegativity. It has a higher electronegativity, which means that oxygen is going to have a stronger pull on its shared electrons. And I'm going to represent that by an arrow. So this pair of shared electrons, which is shown here in the straight line between the oxygen and hydrogen, I'm going to show that oxygen has a stronger pull on those electrons. It has a stronger attraction to those electrons. And what actually I think we can also do, especially as we're just talking about this for the first time, I'm going to place those electrons, just these little E's, our abbreviation for electron, closer to the atomic nucleus of oxygen. So we can remember that oxygen has the higher electronegativity, it's going to have a stronger attraction, and those shared electrons are going to spend more time closer to the atomic nucleus of oxygen. Now again, these electrons aren't set in this one position. They are moving around their kind of overlapping shell, but in reality, they're going to spend more time closer to that oxygen atom. Now, we also have another oxygen-hydrogen bond here in the water molecule, and this other bond has the same concept. We're going to see that oxygen has a higher electronegativity than hydrogen, which means it's going to have a stronger pull, attraction to those shared electrons, which is represented by the red arrow. Again, I'm going to place those shared electrons closer. Hopefully we can see that that's an E. I'm going to place those shared electrons closer to that oxygen atom, denoting it has a stronger electronegativity. Now, we recognize electrons have a negative charge associated with them. And when those pairs of electrons spend more time kind of associated with one atom versus the other, that atom with a higher electronegativity is going to get a partial negative charge associated with it. And we designate the term partial as a Greek delta symbol. So this is partially negative. That's what we're saying here. And as a consequence, because these two electrons are spending more time near the atomic nucleus of oxygen with their negative charge, giving oxygen a partial negative charge, hydrogen is going to get a partial positive charge because those two electrons are spending their time farther away from the atomic nucleus of hydrogen. And this is what causes polarity, kind of an unequal distribution of those shared electrons between the atoms that are sharing them. Now, we could do the same thing for the other covalent bond that's part of the water molecule. Since the other pair of shared electrons are spending their time closer to the atomic nucleus of oxygen most of the time, oxygen is going to get a partially negative charge due to those electrons being negative, and hydrogen is going to get a partial positive charge due to the fact that those electrons are spending more time closer to the atomic nucleus of oxygen due to its higher electronegativity than they are to hydrogen. And because water is so small, it's made out of 3 atoms, and both bonds, in both covalent bonds in water are polar covalent bonds, we are going to designate this entire water molecule as polar. We have both covalent bonds that are associating the oxygen and 2 hydrogens are polar covalent bonds. Now, these polar covalent bonds came about because of unequal sharing of electrons between the oxygen and hydrogen. And that's really a basic definition of polar covalent bonds, unequal sharing of electrons. And because the shared pair of electrons are shared unequally, this creates polarity, a partially negative charge associated with one of the atoms sharing that pair of electrons, and a partial positive charge on the other atom in the covalent bond. Now, whenever you have an oxygen that is covalently bonded to a hydrogen, because the oxygen has a higher electronegativity than hydrogen, it is always going to form a polar covalent bond. So we can look at it in terms of water, but we can also look at it in terms of a different kind of collection of atoms. So I can use a carbon atom, and maybe this carbon is covalently bonded to an oxygen and a hydrogen. We're going to learn in a couple of modules that this is called a hydroxyl group. And it doesn't matter if I draw this as an oxygen next to a hydrogen. What I mean here is that this oxygen that's covalently bonded to the carbon is also covalently bonded to that hydrogen. So there is a covalent bond that is between this oxygen and hydrogen atom. We just don't show it. Now we know carbon can make 4 covalent bonds, so I'm just going to make the other covalent bonds to hydrogen atoms. So now we have an oxygen and a hydrogen in this particular molecule, and we can apply the same concept that we just reviewed for water to this hydroxyl group. Oxygen has a higher electronegativity than hydrogen. The shared pair of electrons are going to spend more time near the oxygen atom due to oxygen's greater attraction for that shared pair of electrons. Because those electrons are negatively charged, that oxygen is going to get a partial negative charge associated with it, and hydrogen is going to get a partially positive charge associated with it. So I don't want you to think about polarity just in the concept of water. We can apply the concept of polarity that we discussed and focused on in water to other molecules that also have oxygens and hydrogens covalently bonded to one another. When we think about atoms that are going to produce polar covalent bonds that are part of our biological molecules, then two atoms that we really want to focus on are oxygen and nitrogen. Those two atoms have a very high electronegativity compared to other atoms on the periodic table and other atoms that make up our biological molecules. So a polar covalent bond, an example of that would be an oxygen that is covalently bonded to a hydrogen atom. In addition, nitrogen also has a high electronegativity, a high attraction for its electrons. And if you have a nitrogen bound to a hydrogen, this is also going to form a covalent bond. Both oxygen and nitrogen have higher electronegativities than those hydrogen atoms. Oxygen is going to get a partial negative charge, hydrogen a partial positive. We've seen this. But also in the context of nitrogen being covalently bonded to a hydrogen, the nitrogen is going to get a partial negative charge, and the hydrogen gets a partial positive charge. Polar covalent bonds are also formed when oxygens bind to carbon atoms and nitrogens covalently bond to carbon atoms. Oxygen and nitrogen, again, with their higher electronegativity, have a higher electronegativity as compared to carbon. So oxygen, again, will have a higher attraction for those shared electrons and have a partial negative charge, where carbon is going to have a partial positive charge. And then we can say the same thing for nitrogen. It has a higher electronegativity compared to that carbon atom, and it is going to attract its electrons stronger than that carbon atom. Now, so far we've focused on polar covalent bonds, but what atoms would make up a nonpolar covalent bond? Well, anytime an atom is bound to itself, two of the same atoms sharing electrons in a covalent bond, that is going to be a nonpolar covalent bond because both atoms have the same electronegativity. They're going to have the same attraction for that shared pair of electrons. So anytime you have a hydrogen-hydrogen, a carbon-carbon, an oxygen-oxygen, a nitrogen-nitrogen, these are all going to be nonpolar covalent bonds. And there are no charges associated with the atoms that are part of a nonpolar covalent bond. Because the electrons are shared equally, the electronegativity of the atoms are the same, there are no partial charges that result. So again, that represents kind of a basic definition of a nonpolar covalent bond: equal sharing of electrons between the atoms that are sharing them due to equal electronegativity. Now, it doesn't always have to be the exact same atom in the covalent bond. A carbon-hydrogen bond is also considered nonpolar. Now, the carbon atom and the hydrogen atom don't have the same electronegativity, but they're similar enough that they form a nonpolar covalent bond as they share those electrons equally. And we can look at any example of this. I'm just going to create what I'm going to call a carbon skeleton. Carbon skeleton is when you have several carbon atoms all linked together by covalent bonds. And if I fill in the valence shells of each of these carbons with hydrogens, this would be a nonpolar molecule. All of the atoms involved in this molecule that are sharing electrons share electrons equally. And there are no partial charges when atoms are sharing the electrons equally, because we can think about the electrons kind of being equidistant from the between the atoms that are sharing them. And so they are not distributed closer to one atom versus another, and we create these nonpolar covalent bonds. I'm not going to do them for all of these, but you get the idea. Anytime you have a substance or part of a molecule that is just made up of carbon and hydrogen atoms like we have here, this is what we call a hydrocarbon. The hydrocarbon is always going to be nonpolar because it is always going to contain just carbon and hydrogen atoms, which are sharing electrons equally. It doesn't matter the size, the length of the carbon skeleton, or how many hydrogen atoms you need to fill the valence shells of all those carbons. Anytime you have a hydrocarbon, it is going to be nonpolar. I hope this review of nonpolar and polar covalent bonds allows you to apply these concepts to more complex molecules to determine if any of the atoms carry partial charges on them due to an unequal sharing of electrons. And these concepts, this kind of concept of polar and nonpolar covalent bonds, is going to come right back to us because this is going to determine whether a molecule is soluble in water.